All right, today we are going to crack open a legendary physics book to tackle one of its most classic challenges. It's one of those problems that seems super simple on the surface, but solving it, oh, it's so satisfying. So let's just dive right in.
You know that feeling, right? You think you found a genius shortcut, but it ends up taking way longer because of, I don't know, a slow tractor or terrible road conditions. Well, that's exactly the puzzle we're tackling today. It's all about finding the path that takes the least amount of time, which, spoiler alert, is not always the shortest one.
So where does this problem come from? Well, it's from Irodov's Problems in General Physics. Now, if you've studied physics or engineering, you probably just got a little shiver down your spine. This book is an absolute legend. We're talking almost 2,000 super tough problems. It's a rite of passage, you know? It's basically the final boss of physics homework.
And to guide us on this quest, we're going to take advice directly from the man himself, Irodov. Right in the preface, he gives us the master key. He says, solve each problem in the general form. What does that mean? It means using letters, variables, not just plugging in numbers. And honestly, that's where the magic is. You get to see the real beauty of how everything connects. So that's exactly our game plan.
Okay, let's get specific. The challenge we're taking on is problem 1.17. This is a classic optimization puzzle, and it's just a perfect example of why setting up the problem the right way is half the battle.
So here's the scenario. Picture this. You're driving along a perfectly straight highway. You're at point A. Your destination, point B, is out in some field off to the side. Now your car can zoom on the highway, but once you hit the field, you're going to be eta times slower. You could just think of eta as like a slowness factor. The big question is, to get to B as fast as humanly possible, where do you turn off the highway?
And here's a picture of what we're talking about. See, you're cruising from A to some point C on the highway. That's your turnoff. Then you cut across the field from C to B. Now, that point D on the road is directly opposite B, and that distance between them is L. The mystery distance, the one we need to figure out, is from C to D. We're going to call that X.
All right, time to follow Irodov's code. First things first, we have to translate this picture, this whole scenario, into the language of math. We've got to set up our variables. This is how we solve it in that beautiful general form he talked about.
Okay, let's slam all out. V, that's our speed on the nice smooth highway. In the field, our speed gets knocked down by that slowness factor, eta. So our speed is just V divided by eta. Simple enough. L is that straight line distance from the highway out to point B. And then there's X. X is the star of the show. That's the turnoff distance we're trying to find. That's our unknown.
Okay, now for the really cool part. We're about to build one single equation, just one, that will tell us the total travel time for the entire trip. And it's all going to depend on that one choice we make, X.
We'll call it T of X. T for time, and it's a function of X because the time changes depending on where we turn off. And look, we're not just looking for any travel time. We're on a quest for the best time, the optimal time. We need to find the one single value of X that makes our total travel time as small as it can possibly be. We're looking for the minimum.
So how do we build this thing? It's pretty straightforward, actually. Total time is just the time on the highway plus the time in the field, right? And we all remember from school, time equals distance divided by speed. So, for the highway part, the distance is whatever the total length AD is, minus our little x, and we divide that by our highway speed, v. For the field part, well, the speed is v divided by eta. The distance, that's the tricky bit. But look at the diagram. It's just the hypotenuse of a right triangle with sides L and x. So hello, Pythagorean theorem. The distance is the square root of L squared plus x squared.
Okay, so we have this big equation for time. How in the world do we find the minimum value? Well, anytime a mathematician or physicist hears the word minimum or maximum, their brain immediately screams one thing: calculus. It's the perfect tool for this, and our roadmap is super clear. Step 1, find the derivative of our time function. Step 2, set that derivative to 0. Step 3, solve for x. That's it. That's the plan.
So, we do the calculus, and this is what we get. Now, what does this big messy thing, this dt over dx, even mean? Well, think of it like this. It tells us how our total travel time changes as we wiggle our turnoff point x back and forth. It's the rate of change. Is our total time getting longer or shorter as we move our turnoff point? This equation tells us.
So if we want the absolute fastest time, we're looking for that perfect sweet spot where the time stops getting shorter but before it starts getting longer again. It's that moment of perfect balance. And at that exact point, what's the rate of change? It's 0.
So we take our big derivative equation, we set it equal to 0, and now it's just algebra. We just have to solve for x.
And after we rearrange everything, we get this. Look at that. It's so clean, so elegant. The perfect turnoff distance, x, is just L divided by the square root of 8s squared minus 1. And the incredible thing is, this one little formula works for any speed, any distance L, any slowness factor eta. It's the universal answer.
Okay, moment of truth. Does our answer match the one in the back of the legendary Irodov book? Let's see, and bam! It's a perfect match. See? That is the power of following his advice. We didn't just stumble upon the answer. We built it from the ground up, and we understood every single step.
So you might be thinking, okay, cool car problem, but what's the big deal? Well, the big deal is that this isn't just a math puzzle. It's a window into a really deep principle that runs through all of physics and science. It's called the principle of least time. And it basically says that nature is, well, kinda lazy, in a good way. It always tries to find the most efficient path, the path of least resistance, or in this case, least time.
And once you see it, you start seeing it everywhere. Why does light bend when it hits water? It's not magic, it's actually solving this exact same problem. It's finding the fastest path. How do companies like Amazon figure out the best delivery routes? They're solving for the least time. Think about animals in the wild. They instinctively take paths that save the most energy. Even the internet. The data packets carrying this very explainer to you are zipping around the globe trying to find the quickest route. They're all, in a way, solving Irodov's problem 1.17.
So I'll leave you with this thought. We're always told the shortest distance between 2 points is a straight line. But we just proved that the fastest path often isn't a straight line at all. It takes a little bit of strategy, a little bit of math. So my question for you is, where in your life or your work is the straightest, most obvious path not actually the fastest one? Something to think about. Thanks for geeking out with me today.